Hi guys, welcome back to the channel. A quick update on the simple radio project. I wrote an interface for the analog to digital converter for the LTC2314. It's basically this part, it's quite simple. It has an SPI interface where you're shifting out the previous conversion. But how it works, it needs 16 clock cycles to shift out the result. But it needs another 3.5, 4 clock cycles to idle to prepare for the next conversion and probably to run some internal stuff. Anyway, so it has 3 methods of accessing the data. I choose the third one, which is you'll see it on my blog, which is the simplest one, which needs 20 clock cycles, full clock cycles, and you can keep the serial clock running continuously. It was the easiest way to write it, and I'm lazy, and it is what it is. Anyway, the code is made of 3 parts. So it's the actual interface, which is going to send the chip select and the clock to the actual IC external to the FPGA, and it's going to sample the incoming serial data. Now, in order to test this, I wrote a model in VHDL with the close behavior of the actual part. So I wanted to test this before I even commit to making PCBs, and so I made a model, a rough model of how the part works and is shifting out data, and I created a table of samples, so it's actually shifting out a sinus waveform. It's sending 16 samples and then it's repeating itself. But anyway, it's quite simple. I use a little bit of AI to create the actual samples, the table, the ROM with the samples. It's nothing fancy. You can see the code. All the code is available on my blog. I'm going to link it in the description. And that's it. It's nothing fancy. Yes, the model is actually synthesizable. You can put it on FPGA, and this is what I'm planning to do before I even commit to build the front end. So I'm going to use it as a signal generator to impersonate the ADC. So yeah, that's it. Let's go straight to simulation. Okay, very quick, the simulation. So what do we have here? This is the test bench, which is instantiating our interface, our LTC interface. And this is the model, which is creating, let's say, fake samples like the chip is actually attached. So I'm going to start the simulation, if I remember how. Yeah, here, bam. And I'll go 1 microsecond in steps of 1 microsecond. And you see here a nice waveform is showing up, right? So if I zoom in here to see a transaction, you see this is the chip select. So the chip select goes down the part. So when the chip select is high, the part is in high Z, high impedance, and it's starting to shift out those 16 bits. And then, so a cycle is basically 20 clock cycles, a full cycle, conversion cycle. So let's say it starts here. So when the chip select goes down, it stays high for 16 cycles, and then it goes up. So during those 16 cycles, the previous conversion is getting shifted out of the part. And then there are 4 other cycles which are to have enough time for the conversion for the everything. So this is a full cycle, like from here to here, 20 clock cycles, right? So if we feed this core with the 80, I say core, but it's going to be an actual device. So if we feed this part with the 80 megahertz clock, a conversion cycle is 20 clock cycles. So this will lead to a sampling frequency of 4 megahertz. Okay, so it's not much to say about this simulation. It's just this, right? So this block here, the model, is creating this nice waveform. Now I created a model that you have a signal you can actually force to have a sinus, or you can force to have like a constant value. I'm not sure why I did that, what for. But anyway, it's not much. The model is actually synthesizable. You can actually put it on FPGA, inside the FPGA, and play with this without actually having the ADC attached. So you will get this sinus, like a test signal. Again, all the code on the blog, you can download the code. It's not much. I think the zip file is something like 4 kilobytes. Very, very small, easy to understand. Some of the code I wrote with a little bit of help from our friends from AI. The model, I tried to actually write it with AI, and I got a horrible code which I had to rewrite myself in a very simplistic way. AI actually helped me with, I'm going to show you, AI helped me with to generate the sinus pattern, the sinus, sorry, pattern here, the values, 14-bit values. This was very, very helpful. So I have here like a constant pattern or a constant value, and I have this one, and it's controlled by this pin here, which is, if it's 1, it's going to spit out the sinus. If it's 0, it's going to give you a constant value. Anyway, not much. You can see here it's less than it's one screen, and the same thing with the actual core. The interface is actually less than a screen. Okay, that's it. You can download, you can simulate, you can do whatever you want with it. I'll finish with this. Okay guys, so after the simulation, what is going to follow, probably tomorrow, I'm going to put it on the FPGA and give it a go, see how well it works in real life, and I'll try to capture inside the core, inside the FPGA. I'll try to capture those samples which are coming from the model through the interface. I'll capture them inside with the ILA, Integrated Logic Analyzer, or chipscope, how we call it back in the day. So that would be the next step. I hope you enjoyed the video, and have fun.